Welcome to Part C of Week 6. In Parts A and B, we learned how to write powerful SQL queries using the aggregate functions and group by and having and subqueries. But now we turn to a different important question: how to make those queries run most efficiently. And that's what this section covers: database indexing and query optimization. These are the skills that separate someone who can just write SQL from someone who can write SQL that performs and can perform on large, real healthcare databases possessing millions of records. If you ever work with an EHR system or a claims database or a clinical data warehouse, understanding indexing is not optional, it's essential. So what are our objectives for this part? In Part 6C, you should be able to accomplish 6 things. Here they are. First, understand what database indexes are and why they matter for query performance. Second, learn the B-tree index structure, and that doesn't stand for binary. It's balanced tree, which is PostgreSQL's default and the one that you will encounter most often. Third, you'll be able to create different types of indexes including the single column, multi-column, partial indexes. Fourth, you'll be able to read and interpret the output of explain and explain analyze, which are PostgreSQL's tools for showing you how a query will be executed. Fifth, you may be able to identify the difference between sequential scans and index scans in a query plan. And finally, sixth, you'll be able to apply practical optimization strategies to healthcare databases so that your queries run efficiently even on very large data sets. All right, this first section introduces the concept of indexing. Think of this as the performance engineering side of a database. Writing correct SQL is step 1, but writing correct SQL that executes efficiently on tables with hundreds of or thousands of or even millions of rows is step 2. Indexing is the primary tool we use to bridge the performance gap. What happens if you don't have an index? Let's start with understanding the problem. When you run a query with a where clause and there's no index on the filtered column, Postgres has no choice but to perform what's called a sequential scan. That means it reads every single row of the table, one by one, to check whether each row matches your condition. For a table with just 10 rows, it's fine. Happens instantly. But think about our xHealth database. The encounters table has over 10,000 rows. A sequential scan on that table is noticeably slower. Now imagine a real hospital system with millions of encounters. A sequential scan on a million-row table is unacceptable for any interactive application. So the analogy I want you to remember is the phone book. If you need to find someone named Johnson in a phone book, you not start on page 1 and read every single name. You flip to the J section because the phone book is already organized alphabetically. Well, that alphabetical organization is essentially what an index does for a database. Without it, you're reading every page. Look at the performance impact on the slide. As the number of rows grows, the time for a sequential scan grows linearly, directly, proportionally. And this is the fundamental problem that indexing solves. So what exactly is an index? An index is a separate data structure that Postgres creates and maintains alongside your table. A lot of people refer to this as metadata. Instead of it being the actual data, it's data about the data. It stores sorted references that point back to the actual data, which is stored in a different location. The index is separate from the actual data. So think of it like the index at the back of a textbook. The index itself does not contain the full content. It just contains organized references to help you find the content. It tells you exactly what page to turn to. Well, here are the 5 key points to understand. First, an index is a separate structure. It does not change your data. It exists alongside it. Second, like a book index, it provides organized lookups that point to the right location. And third, it speeds up select queries, specifically where clause filtering, join conditions, and order by sorting. And fourth, Postgres automatically creates indexes for primary key and unique constraints. It does this for you automatically behind the scenes. So your primary key is going to have an index, and any column that has unique constraints will have an index, a B-tree index. In our ex-health databases, patient ID already has an index in the patients table because it's the primary key. Fifth, and this is the trade-off you need to understand, indexes make reads faster, but writes slower. Let me say that again. Indexes make a read faster. It can locate a record, a row, much more quickly. But when you're writing a new row, when you're adding data, inserting data, then it has to update the keys, the indexes, for each of the fields that you've instructed to index. And so that every insert, every add is going to take the time necessary to maintain the indexes. So inserts, updates, or deletes require maintenance for the index. So Postgres has to update not just the table, but also every index associated with that table. Indexes are not free. They have a significant maintenance cost. The bottom line, indexes do not change the data. They create an optimized lookup structure alongside the table. Now let's look at the specific index structure that Postgres uses most often, and by default, if not otherwise specified. It's called the B-tree. Let's make an important clarification. B-tree stands for balanced tree, not binary tree. This is a common misconception. When you see B-tree, you say, in computers, it's probably binary. No, this is a balanced tree, and it's been well studied and well developed, and that's why Postgres uses it. The structure works like this. At the top, you have a root node where you start any search. Below that are branch nodes. At the bottom are what are called leaf nodes that have no further direction down the tree. So the data is maintained in sorted order throughout the tree. When you search for a value, you start at the root, and if it says it's less than, then you go to the right. If it's greater than, you go to the left. You start at the root and follow the pointers down through the branches until you reach the leaf node that corresponds to the pointer that you're actually searching for, hitting your target. Because the tree is balanced, every search along the path from the root to the leaf is the same length, and so each time you do a search, you're going to cut the possible remaining rows in half. So the B-tree supports all the common comparison operators like equals or less than or equal, greater than, between, in, and even like with a prefix such as like, Smith, % with a wildcard, but it will not help with the like phrase if the wildcard is at the beginning, because we will need to, well, we'll get into that a little bit later in depth, but your index structures are somewhat complex, and it's going to take us a little while to go through all the different varieties and figure out which index you need for which circumstance. Well, what's the key performance metric to understand? The B-tree search time is in the order of the log of n, where n is the number of records. So that means it's a logarithmic scaling. So look at the comparison on this slide. With a sequential scan, searching 10,000 rows requires 10,000 comparisons in the worst case. But with a B tree index, that same search requires roughly 14. That's because log to the base of 2 of 10,000 is approximately 13.3. Well, that's an enormous difference. And it only grows as the data gets much larger. For 1,000,000 rows, a sequential stand needs 1,000,000 comparisons, while a B tree needs only about 20. Postgres actually supports several index types, even beyond the B tree. In this table, you can see an overview. The B tree is the general purpose default and handles most queries. The second one, hash, indexes are optimized for equality only comparisons, not for less than or greater than or alphabetical. Equality only comparisons, but do not support the range queries. Gen, which stands for generalized inverted index, is specialized for arrays or a full text search and JSON-B data. Gist is used for geometrical and range data types, which you might encounter in spatial queries. And BRIN, which stands for block range index, is very efficient for large tables where data is physically sorted, such as time series data, where newer records are always appended at the end. So the data is partially already sorted naturally. So for this course, we focus entirely on the B tree. That's the one that's used most frequently, and that's exclusively what we will be utilizing. The others are highly specialized tools that you would encounter in very sophisticated situations. But the B tree covers the vast majority of the use cases that we will see in healthcare. All right, so we've recognized we're going to have a need for an index. What do? Let's look at the syntax we have. We actually have commands to create indexes, and there are 4 variations that we'd like to go through. Each serves a unique, different purpose. The first is simple, a single column index. Create index, then the name for that column. And on the table, the name of the table, with the column in parentheses. Notice the naming convention, IDX underscore table name underscore column name. This is a widely adopted convention. It's not a law, it's not required, but it's used so frequently you need to be familiar with it. I recommend that you follow it. It makes it immediately clear what each index is for. What is the second? The second is a unique index. Adding the unique keyword means Postgres will enforce that no 2 rows can have the same value in that column. And this is useful for columns like NPI numbers on the providers table, where every value must be unique, can't have duplicates. The third is the multi-column or composite index. Here we are indexing on 2 columns together, kind of merged, compound index, like patient ID and encounter date. This is particularly useful when queries frequently filter on both columns simultaneously together, such as finding all encounters for a specific patient within a certain date range. The order of columns in a composite index matters. The order matters. The index can be used for queries that filter on the first column alone or on both columns, but it's not helpful for queries that filter only on the second column. And finally, the fourth is an expression index. Instead of indexing a column directly, we're indexing on the result of an expression, like in this case, extracting the year from the date of birth. This is useful when your queries frequently apply a function to a column using the where clause. What are partial indexes? Partial indexes are one of the more elegant features in Postgres. Instead of indexing every row in a table, a partial index only indexes the rows that match a specified where condition. So let's look at this first example. We create an index on last name, but only for rows where isActive equals true. That makes sense, doesn't it? So if our application almost always actively queries only for active patients, this index is smaller and it uses less storage and it's faster. Let's look at our second example. It indexes the ICD-10 code, but only for chronic diagnoses. If quality reporting queries consistently filter on isChronic equals true, then this partial index is perfectly targeted. It's optimized. The critical thing to understand is that for Postgres to use a partial index, the query's where clause must match the index's where clause. If you create a partial index on active patients, but your query does not include the where isActive equals true, Postgres will not use that index. The conditions have to align precisely, exactly. So partial indexes are an excellent tool when you know your queries follow consistent patterns. And this is common in healthcare applications, where workflows are highly standardized. So when do we want to index and when not? Indexing is not about creating an index on every column. That would actually hurt performance. You need to be strategic. And this slide gives you some of the decision framework. You should create indexes when a column is frequently used in where clauses, join conditions, or order by sorting. Indexes are most beneficial on large tables with thousands or even more rows. And they work best when the column has high selectivity, meaning many unique values. A column like patient ID with 500 unique values is an excellent candidate for an index. Every lookup narrows down to a small subset of rows. You should avoid indexes in certain situations. Like small tables with under 100 rows, they don't benefit much because Postgres can scan a 100-row table quite quickly. And creating and maintaining the index incurs overhead. Also, columns that are rarely used in queries just waste storage. Tables with very heavy write operations, lots of updates, lots of inserts, lots of deletes, pay a higher cost for each index because every write must update every one of the indexes. Also, columns with low selectivity, like a Boolean flag that's true for 95% of rows, they do not benefit from indexing because the index does not narrow the search meaningfully. And if a column is already the leftmost column in an existing composite index, a separate single column index is somewhat redundant. So let's read some query plans. The explain and explain analyze. We're going to move on to one of the most practical skills in database work, of reading a query execution plan. Explain and explain analyze are Postgres' tools for showing you exactly how a query will be, or was, executed. If indexing is about building the optimization, explain is about verifying that the optimization is actually being used. And you really should never assume an index is being used. Always verify with the explain. Explain is the non-destructive version. You put explain before your select statement, and Postgres returns the execution plan it would use without actually running the query. This is safe to use on any query because it does not execute anything. Let's look at this example. We run explain on a select from patients where last name equals Smith. The output shows a seq scan on the patients table, which means Postgres is performing a sequential scan, reading every row. The cost, numbers 0 to 1450, represent Postgres' internal estimate of the work required to perform this. The first number is the startup cost, how to get ready, and the second is the total cost. These are not in milliseconds or any real units. They're just relative cost units that query planners use to compare different execution strategies. The rows estimate of 3 means Postgres thinks about 3 rows will match. The width of 246 means each returned row is estimated at 246 bytes. And the filter line shows what condition is being applied to each row during the scan. Here we can see that it is filtering on the last name equals Smith. And the key takeaway from this output is that we're doing a sequential scan, which means there's no index on the last name being used. Explain analyze, the actual execution statistics. Explain analyze goes further. It actually runs the query and then reports both the estimated plan and the actual execution statistics. This gives you real timing data instead of just estimates. Let's look at the output. Now we have 2 lines of numbers. The first line shows the estimated values, just as in the previous slide. But the second line, in parentheses, starting with actual time, shows what really happened. The actual time of 0.015 to 0.089 tells us the first row was found after 0.015 milliseconds and the last row after 0.089 milliseconds. The rows equals 3 confirms that 3 rows were actually returned. Loops equals 1 means the scan was executed only once. Below that we see rows removed, filter, 497. This is very informative. It means Postgres read 500 total rows, our entire patient's table, and threw away 497 that did not match the filter. Only 3 survived. That's a lot of wasted work, and it tells us an index would have been highly beneficial in this use case. Planning time and execution time at the bottom give you the total wall clock time. Planning time is how long it took to figure out the execution plan, and execution time is how long the actual query took to execute. Let me give you one important warning. Explain Analyze runs the query. So if your query is an update or delete, it will actually modify data. So always wrap those in a transaction with begin first and rollback after, so you can safely see the plan without any persistent changes to your data. Understanding query plan components. This reference table lists the key components you will see in Explain output. And let me highlight the most important issues. Seq scan means a sequential scan, reading every row. When you see this on a large table, it's usually a signal that an index might help. Index scan means Postgres is using an index to find matching rows and then fetching the full row data from the table. This is what you want to see for selective queries on large tables. Now, an index-only scan is even better. It means all the data the query needs is contained in the index itself, so Postgres does not even need to go out to the table to retrieve the rows. Now, bitmap index scan is an intermediate approach, where Postgres uses the index to build a bitmap of matching row locations and then fetches them from the table. This is common when a query matches a moderate number of rows, too many for a simple index scan, but few enough that a sequential scan would have been wasteful. And the cost numbers are estimates, not real time. Use them to compare different plans, not as absolute measurements. Rows removed by filter is particularly useful because it tells you how many rows Postgres had to read and discard. A high number here on a large table is a strong signal that you need an index. What is the impact of indexing? Let's look at before, when there is no index, and after, once we've created the index. On the left, we run an Explain Analyze on a query filtering encounters by patient ID, and it equals 42 with no index. Postgres performs a Seq scan The actual time stretches to 15.432. It removes 9,982 rows by filter, meaning it read nearly all the 10,000 rows just to find the ones for patient number 42. Total execution time was 15.5 milliseconds. On the right side, we create an index on encounters for patient ID and then run the same query. Now Postgres performs an index scan. The actual time drops to 0.089. Execution time down to 0.112. That's 150 times improvement from a single create index statement. So now 15 milliseconds might not sound so terrible in isolation, but think about a real application. A provider opens a patient chart, the system runs dozens of queries to load encounters, diagnoses, medications, lab results, and claims. If each query takes 15 milliseconds instead of 0.1, those delays compound. Multiply that across hundreds of concurrent users, and you have a system that feels sluggish. Indexes are what make interactive applications responsive. Again, the scan types in Postgres. Let's consolidate the four main scan types you will encounter in your query plans. A sequential scan reads every row in the table. It's used when there's no relevant index, when the table is small enough that an index would not help, when the query needs most of the rows anyway. A seq scan is not always bad. For small tables like our 33-row provider table, a seq scan is likely faster than an index scan because the overhead of traversing the index exceeds the cost of just reading the 33 rows. An index scan traverses the B tree index to find matching rows, then goes out to the table to fetch the full row of data. And this is the most common scan type for selective queries on indexed columns. It is most effective when the query is looking for a small fraction of the existing rows in the table. An index-only scan is the fastest type. All the data that the query needs is already in the index. It's part of the index. So Postgres never has to go out to the table at all. You get this when your select columns and where columns are all part of the index. And then the bitmap. The bitmap heap scan is a two-step process. First, Postgres scans the index and builds a bitmap of matching rows. Then it uses that bitmap to fetch the rows from the table. This is most efficient when the query matches a moderate number of rows, and is common when multiple index conditions are combined, like with an AND or an OR. What's the key takeaway? Key takeaway is that seeing a seq scan does not automatically mean something is wrong. Context matters, but if you see a seq scan on a large table for a selective query, that's an opportunity to improve your optimization. So what are the recommended indexes for our xHealth database? Let's take a look. Let's apply what we've learned so far about our indexes. This table shows the indexes that I recommend creating for a typical healthcare query pattern. The encounters table needs indexes on patient ID, provider ID, encounter date, and the patient ID is the most common. It's most commonly used in the join and other filter columns because almost every query starts with a specific patient. Provider ID supports provider performance queries. Encounter date supports date range queries, which are used in virtually every encounter reporting context. How about the diagnosis table? The diagnosis table needs indexes on ICD-10 code for diagnosis lookups and encounter ID for joining back to the encounter. How about the medications table? It needs an index on patient ID for medication, for any medication histories, any medication inquiries. Lab results benefit from a composite index on the patient ID, the LOINC code, since lab queries almost always specify both which patient and which test. And finally, for the insurance claims, you're going to need index on the patient ID and claims by patient inquiries. There's an important note at the bottom of this slide. Primary keys already have indexes automatically in Postgres, but foreign keys do not get automatic indexes. This is a common surprise. In many other database systems, foreign keys are automatically indexed, but not in Postgres. You have to create those manually with your own code. This is exactly why the encounters.patientID index is so important. Patient ID is a foreign key referencing patients, but Postgres does not index it by default. All right, let's look at our query optimization strategies. Let's broaden from indexing specifically to query optimization in general. Here are the 7 strategies ordered from most to least impactful. First, always start by using explain analyze to understand the current query plan before you try to optimize anything. Don't guess, measure. Second, create indexes on columns used in where, join, and order by clauses. This is the single most impactful optimization opportunity in most cases. Third, be specific. In your select clause, do not use select star when you only need 3 columns. Select star forces Postgres to fetch all columns from the table, which means more data read from the disk, more data sent over the network, and it prevents index-only scans because the index likely does not contain every column. And fourth, filter early with where clauses to reduce the data set before the joins and aggregations. The fewer rows that flow through the rest of the query, the faster everything will operate. Fifth, avoid applying functions to index columns in where clauses. If you write where upper of last name equals Smith, Postgres cannot use a B-tree index on the last name because the index stores the original values with whatever case was typed in, not fully uppercased versions. So you can either store the data consistently or create an expression index when you create that index. 6, use limit when you only need a subset of results. If you just want the 10 most recent encounters, adding a limit to 10 with an order by lets Postgres stop instead of processing every matching row. And finally, 7th, run analyze after large data changes. Postgres maintains internal statistics about data distribution, and it uses those statistics to choose execution plans. After a bulk insert or update, those statistics can become stale. Running analyze refreshes them to the query planner and makes for better decisions. What can slow down your queries? Select star on large tables wastes resources by reading columns you don't actually utilize. Missing indexes on frequently filtered columns forces sequential scans, which are time-consuming. Applying functions on index columns like where upper of name equals Smith prevents the index from being used because the B tree stores those original values, not the upper. Leading wildcards, a leading wildcard in the like patterns, such as like %Smith, cannot use B tree because the index is sorted from left to right, and the leading wildcard means you can't start in any particular order from an alphabetical sort perspective. What about OR conditions? OR conditions can sometimes prevent index usage because Postgres may not be able to combine 2 separate index lookups efficiently. In some cases, rewriting the query as a union of 2 simpler queries each of which can use an index, might perform much better. Outdated statistics lead the query planner to make poor decisions. If the planner thinks a table has 100 rows when it actually has 100,000, it might choose a sequential scan when an index scan would be far better. Running analyze fixes this. And finally, over-indexing. Every index you add makes insert, update, and delete operations slow down, because each write must update every index. Creating 20 indexes on a single table would make every write operation slow down. Be strategic. Index what your queries actually need. Now, what about index maintenance? Indexes are not something you create once and then forget. They require ongoing maintenance. And here are the 4 tools that you can use. As we've talked about, analyze. It updates the statistics on the query that the query planner uses. You want to run it after any bulk data loads or changes, any large deletes, any operation that might significantly change the distribution of the data. What about vacuum? What does the vacuum do? Well, vacuum reclaims storage space from rows that have been deleted or updated. In Postgres, when you delete or update a row, the old version is not immediately removed. It's marked as dead, but still taking up space. So vacuum cleans up those dead rows. And without regular vacuuming, tables and indexes become bloated, using more disk space and making scans slower. Postgres runs auto vacuum in the background, but you should understand what it does. What about a reindex? Reindex rebuilds the indexes from scratch. And this is useful when an index becomes bloated or corrupted, which can happen over time, especially with heavy write activity. Rebuilding creates a fresh, compacted, ideal index. And finally, page stat user indexes is a system view that tells you how often each index is being used. The index scan column shows how many times an index has been used since the last statistics reset. This is invaluable for identifying which indexes are earning their keep and which are just being overhead. So look at the code examples here. The first runs analyze on the encounters table. The second queries PGStat user indexes to see which indexes are being scanned the most. And the third rebuilds a specific index with a reindex. What about removing indexes that are underutilized? This slide addresses the other side of index management, knowing when to drop an index. As we discussed, every index has a cost. It consumes disk space and slows down the writes. If an index is never being used for reads, you're paying the cost but getting no benefit. The first query on this slide finds potentially unused indexes by checking the PGStat user indexes for indexes where IDX scan equals 0, meaning they have never been used for a scan. It also shows the size of each unused index using pgsize pretty, so you can see exactly how much space is being wasted. The second statement there in our sample shows how to drop an index with drop index if exists. The if exists clause prevents an error if the index has already been removed. Now, there's a few cautions here. First, the usage statistics in PGStat user indexes reset when Postgres restarts, so an index showing 0 scans might just because the server was just recently restarted. Check over a reasonable time period. Second, some indexes might only be used during monthly or quarterly reporting runs. Dropping them because they were not used this week might be a mistake. And third, always verify a development environment before dropping indexes. especially in a production environment. The last thing you want to do is drop an index and then discover that a critical nightly report now takes 10 hours instead of 10 minutes. Let's put everything together with a real-world optimization example. On the left here is a slow query. On the right is the optimized version. They share a same logical goal, dramatically different performance though. The slow version has 4 problems we can identify. First, it uses select star. Remember, that's going to fetch every column from both of these tables. And secondly, it uses the old style implicit join syntax with a comma between table names and the join condition in the where clause. While this works, it's harder to read and maintain. Third, it applies upper to the last name column in the where clause, which prevents any index on last name from being used. Fourth, there are no supporting indexes. Then on the other hand, the optimized version fixes all 4 of those issues. It specifies only the columns actually needed: encounter ID, encounter date, chief complaint, first name, and last name. It uses explicit join on syntax, which is the modern standard and clearly separates join conditions from filter conditions. It removes the upper function and matches the case directly, which allows an index on last name to be used. And it adds 2 supporting indexes, one on patients for last name and one on encounters for encounter date. And the cumulative effect of these changes, they can be quite dramatic. On a large database, you might see a query that took several seconds to drop to a few milliseconds. The changes at the bottom of the slide summarize explicit join, specific columns, removed upper function, added supporting index. Each change contributes, but the index additions typically deliver the biggest improvements. So let's try it yourself. Let's do some practice exercises. Here are 5 exercises to practice what we just covered. And I recommend you doing these in order because they build upon each other. In exercise 1, run the explain analyze on a query that filters the diagnosis table by ICD-10 code. Before you can run it, predict what scan type you will see. Then check your prediction. You should see a seq scan since there's no index on that column pre-existing. Look at exercise 2. Create an index on diagnoses for ICD-10 code. Then rerun the same explain analyze and compare the output. You should see the scan type change from seq scan to index scan, and the execution time should drop significantly. Then the third little exercise. Create a partial index on the encounters table for only completed status encounters. So think about which column to index and what the where clause should be. This exercise practices the partial index concept that we covered in slide number 9. Then, the next exercise, number 4, use pgstat user indexes to find unused indexes in the xHealth database. This practices the monitoring skills from slides 20 and 21. And finally, take a slow query that uses select star and implicit joins and optimize it using the techniques from slide 22. Then run explain analyze before and after to see the level of improvement. Well, let's summarize the 7 key points from this section. Indexes are separate data structures that accelerate the data retrieval by providing sorted lookup paths to the table rows. B-tree is the Postgres default and the most versatile index type, supporting searches like equality, range, and prefix matching operations. And it takes order of log n for search time. Explain and explain analyze are your essential diagnostic tools for understanding how queries are actually executed. You should use them before and after any optimization attempts. Sequential scans read every row in a table, while the index scans are targeted lookups. Understanding when each is appropriate is key to your optimization efforts. Index strategically by focusing on columns used in where, join, and order by clauses. Do not index everything. Avoid over-indexing, because each index adds write overhead for every insert, update, and delete operation. And finally, monitor and maintain your indexes using Postgres system views and tools like Analyze, Vacuum, and Reindex. So what's going to happen next? Next up is the fourth part of this week, the final, where we bring everything together and we'll use the use case and example of population health analytics and HEDIS measures, quality measures. And you'll see how aggregate functions, subqueries, and optimization combine to produce real healthcare quality metrics.